To continue our discussion on orthogonal matrices and the process of orthogonal diagonalization, I present to you the following theorem. The theorem states that the only way that a matrix can be orthogonal is if, and only if, its columns form an orthonormal set. Now, when we derived P using the process of diagonalization, the only thing that we got is that the vectors were linearly independent. Now, this is a much stronger statement in order to create an orthogonal matrix. So let's start with this and see what we can come up with. So here comes a proof. So let's say that we construct P the same way that we construct P typically, which is we take all of the eigenvectors of a matrix A and we turn them into column vectors. We'll assume that there are n of them so that P is an n by n matrix. Now, I would like to ask you to recall that there is a strong correlation between matrix multiplication and the dot product of two vectors, just the standard Euclidean dot product. So if v1 and v2 are column vectors, then taking their dot product, v1 dot v2, is going to be the same as taking the corresponding matrix, v1 transpose, and multiplying by the corresponding column matrix, v2. So this is essentially saying that if you were to take two column vectors and multiply them as matrices, with this one being a 1 by n matrix and this one being an n by 1 matrix, then the corresponding 1 by 1 matrix that you'll wind up with is simply the dot product of these two vectors. So multiply all the corresponding components together, you would wind up with this as a 1 by 1 matrix. So with that in mind, let's continue the proof. The way that we're going to prove that this is orthogonal is the same way that we proved the last matrix was orthogonal. We're going to take P transpose and we're going to multiply it by P. So taking P transpose and multiplying by P. So we take these vectors and turn it into a transpose. So all of these vectors are going to become row vectors, all the way down to Vn. And then for the matrix P, all of these are simply going to remain as column vectors. V1, V2, all the way to Vn. Now we know that the way that matrix multiplication works is we go across a row and then down a column, but that's going to take us right back here to what the typical dot product is. So what this is going to create for us is going to be a rather large array of dot products. So the 1, 1 entry here, we would take the first row here and the first column here and multiply those together. What we wind up with is going to be V1 dotted with V1. For the 1, 2 entry, we take the first row, second column. This will be V1 times V2, and they will be dotted together as well. This will continue on, so forth and so on, until we hit the first row and the last column. This will be V1 dot V sub n. Got a little antsy trying to write that n too soon. The process will be repeated for the second row. We multiply V2 times V1. That'll wind up being a dot product, so V2 dot V1. For the 2, 2 entry, we take the second row, second column, multiply those together. We wind up yet again with a dot product. And continue this over and over until we wind up with V2 dot Vn. Almost did it again. We repeat this process over and over for every single row. And our last row winds up being Vn dot V1, Vn dot V2, and so forth and so on, all the way until we get to Vn dot Vn. Now here's where we can prove the if and only if part. So if we know that P is orthogonal, then this is going to wind up being the identity matrix, which means that every single vector dotted with itself is going to be equal to 1, and every single vector dotted with any other vector is going to be 0. So I guess we can say, note, this product equals the identity matrix if and only if vi dotted with vi is equal to 1, and vi dotted with vj is equal to 0 for I not being equal to j. This is the definition of an orthonormal set. So columns of P form an orthonormal set if and only if P transpose times P is equal to the identity matrix, which again is definition of orthogonal. Now again, the issue that we run into is the fact that when we are generating the matrix P with any old regular matrix, it happens that these columns are linearly independent, not necessarily that they are orthonormal. Now the question becomes, how does a linearly independent set of vectors become an orthonormal set? That's something that was discussed earlier in the course. That process was known as everybody's favorite, the Gram-Schmidt orthonormalization process. Yay! You guys remember how much fun that was, right? Correct answer was no. It was not fun whatsoever. However, our next theorem is going to give us a severe runaround to that process.